Yes, welcome back. So in the previous topics we discussed about the Euler's critical load for the both the ends has been fixed and both the ends having an in support. So what we got as an Euler's critical load. Now we're going to see about the variation of the slenderness ratio for the what the critical loads for the different conditions what we're going to derive or what we have derived. For this how the variation of the limiting stress will be acting, that we can able to find out by using the slenderness ratio, that is limiting stress versus slenderness ratio graph. We can able to find out this. So where you can able to see this as in a critical stress and the critical slenderness ratio, and this is a slenderness ratio, and this is what we call it as a limiting stress versus then a slenderness ratio. That slenderness ratio can be measured by 1 by k, or even the terms or the notation is 1 by lambda also we can able to consider to find out the slenderness ratio. What this the plot shows, that is limiting stress of the f will be decreases when the slenderness ratio increases. The limiting stress f will be always decreases. In fact, when very small, the limiting stress is closely to infinity. So whenever this limiting stress increases or the decreases, it is to be very closely to the infinity, where it is where we cannot able to consider that. So limiting stress can be greater than the yield stress of the material. See, yield stress is nothing but where the maximum where the material can able to withstand the maximum load at the yield point. To identify by using this graph, we have been use this graph as an to find out or to compare the limiting stress versus slenderness ratio. So based on this only we can able to identify whenever the limiting stress is decreasing, the critical slenderness ratio will be increasing. So automatically whenever this critical ratio slenderness ratio increasing, the limiting stress will be rational, where which will be very less. So it will be close to infinity, where which cannot able to consider that. So by using this we can able to consider the yield stress of this particular material. Now what happens, the Euler's formula determines the critical load, not the working load. See, the Euler formulas what we have identified by using that different conditions is critical load. Means it can be identified as a critical load, but we cannot able to consider that as a working load. So that is the reason always we are going to find out the suitable factor of safety for all the material or all the components, which should be whenever we are going to consider the suitable factor of safety for an Euler's derivation is 1.7 to 2.5, where it should be considered to obtain the allowable load. This is how we can able to identify the limiting stress versus slenderness ratio. So now we're going to discuss about the Rankine's critical load. So similarly, how the Euler's critical load is there. Similarly, here we have been also there for an Rankine critical load. So this Rankine critical load is used to find out the or used to validate the relationship between the medium and an long and short columns. So this is just in a comparison, or having an how we can able to identify the loading capacity for whenever it is in the crushing or in a buckling for the both the short, medium and a long columns. So this what this Rankine critical load tells is 1 by PR will be equal to 1 by PC plus 1 by PE. So where PR is nothing but 1 by PR, that PR indicates the Rankine's critical load, and the PC will be equal to FC into A. FC into PC will be equal to FC into A is nothing but crushing load for short columns. So this PC will be equal to crushing load for short columns, and the P is nothing but Euler's critical load. P is nothing but Euler's critical load. Already we have discussed in the Euler's. So pi square into E by L square, that is Euler's critical load for a long column. See, this Rankine critical is nothing but comparison of a relation between all the short columns, medium and long columns. So PR, PC and PE. PR for Rankine critical load, PC is nothing but when a crushing load for a short column, and P is nothing but Euler's critical load for long columns. Now the Rankine Gordon load is used for using the following formulas. What the formulas what we are going to use as in a formulas? This relationship is assumed to be valid for, so this Rankine critical load relationship what we are going to assume is for short, medium and long columns. So this relationship can be used to find out the load carrying capacity. So this Rankine critical load relationship can be used to for a load carrying capacity of a column subjected to crushing or buckling. Now by substituting that PC and P in the above relation, PC is nothing but for an crushing or an buckling for an short columns, and P is nothing but Euler's critical load for an long column. Now by substituting that in that equation, PR FC is nothing by A is nothing but crushing or an buckling load for an short columns by 1 plus Fc into A by pi square E by I into L. So this pi square into E by I L will be equal to U critical Euler's critical load for an long columns. So now by equating these equations, what we are going to get is nothing but by again substituting this equation, Fc by A will be equal to by 1 plus Fc into pi square E by L square into A by L. L is nothing but L will be equal to L. A into I is nothing but a moment of inertia. Since I by A will be equal to R, that is since I minimum by A will be equal to R square. So I by A will be what we can able to replace with the R. So now by considering this Rankine's critical load, that is PR Rankine's critical load equation will become now Fc by Fc into A. Fc is nothing but a crushing or a buckling load for a short column by plus 1 plus all 1 plus A into Le by R whole square. This is the equation what we are going to use to find out the Rankine's critical load. So based on this condition only we can able to find out this. So now we can able to compare this. You can this Rankine equations. What we got is the Rankine's critical load. The main intention of by using this Rankine critical load is to compare the both the short columns and then a long columns, and to identify the relation between the both the short column and then a long columns based on the their given conditions. See, for example, if we take PC is nothing but a short columns, so I'm going to compare with the short columns and with the long columns. Long columns is nothing but Euler's critical load, what we have been derived. So by comparing those relationships between these equations, so the main intention what he has been derived, this Rankine Gordon is derived as in a formula to find out the relationship between both the that is what the Rankine critical load and then a crushing load for a short column and then a Euler's critical load for a long column. So all this we can able to identify, or we can able to find out by using this relation what has been mentioned. By substituting, now we are going to substitute for this PR. PR is nothing but Rankine. By substituting this PC, that is for a short column and then a long column, what we got this, by substituting this we got as an equation. The final equation what we got is nothing but now PR will be equal to Fc into A, that is what for a crushing load, plus 1 into alpha by Le by R into R minimum by whole square, where this I and then a moment of inertia by area will become as a radius of that particular column. So by measuring that into that equation, or by substituting that equations, we can able to find out this Rankine critical load also. So now what we have discussed in this above relations is, we have discussed for an Euler's equation for the both the conditions having any different conditions. Then we have discussed about an slenderness ratio, and then we have discussed about an Rankine's critical load. How we can able to compare the relationship between the short columns and the long columns for an Rankine's relationship. So this is about the some of the topics that what we have been studied in the related to the particularly related to the columns.